accelerate inference in deep neural networks. If there is any question, if you please feel free to interrupt me. Okay, so this is going to be the overview of my talk. So I'll first um, uh, introduce, give a brief introduction to the problem, and I'll also spend some time in describing the setting, and uh, we'll see what roles the compiler can play, and look at specific optimizations like fusion and buffer allocation, and also quickly look at some other optimizations. So before we go, so here are some definitions. So tensors tensors are just like tensors are generalization of arrays. They are just multidimensional arrays. Usually we encounter 1 or 2D arrays often, but tensors are generalizations of that. And we also we'll also be seeing a lot of tensor computation graphs, acyclic tensor computation graphs. They're just data flow graphs that are operating on tensors. So the nodes of the graphs are represent operations on the tensors, and edges represent dependency among operations. We'll look at some examples later. And directed acyclic tensor computation graphs are very common in machine learning inference. So for instance, they have a lot of they're used in many applications like face recognition, object counting, and driverless vehicles, and so on. So with this definitions, we'll see, we'll look at the programming model, and then we'll go into the details. So let's assume that we have a library for deep neural networks. So the library allows us to create directed acyclic graph of primitives. Primitives are predefined operations like convolution, pooling, normalization, deconvolution, etc. So in addition to the ability to create DAGs, the API also allows us to compile a graph and run the graph, say, on a GPU. So we will assume in this talk we'll assume a GPU like setting, and we will assume OpenCL based acceleration. So okay, so this will be the programming model. It's very similar to OpenCL programming model. So it's a single program, multiple data model. So like we have many threads executing the same code. So these threads we can, so they are all organized in a 3D hierarchical grid. So each point in the, I'll show you the, figure. Oh, just give me a moment. I'll share the figure. I'll share my desktop. So can you see my screen now?
Yeah, it's coming up. Yeah,
This one, Rupesh, this
yeah,
grid.
it is visible. This grid is visible. Yes.
Okay, yeah. So the threads are organized in a hierarchical 3D structure. So as you can see, each point represents a work group. So we can see that each point in the grid itself is made up of smaller points. So each point, this big cuboid, that's called a work group. And then the a work group consists of uh, multiple work items. So the smaller cuboids are called work items. So what is special about work groups? So threads in a work group can communicate quickly using what is called as local memory. So and and also each within the work group, we have a notion of wavefront where threads in a wavefront execute in a lockstep fashion. um, so why is this? Because we may, for instance, a work group size, a work group may have 64 threads, but the hardware must support only 32 threads executing in a lockstep fashion. So this is called hence the distinction. So wave threads in a wavefront execute in a lockstep fashion, like uh, SIMD like fashion, and whereas threads within a work group can communicate fast, using local memory. So yeah, that's all I wanted to say about the programming model. So now, can you see these slides? I'm
Yes, Arun.
okay. Sorry. Thanks, Rupesh. So yeah, so inside a work group, a subset of threads called wavefront execute in a lockstep fashion. And one more thing about this, one more comment I wanted to make about the programming model. So many work groups can concurrently execute, and in a GPU, the concurrency is usually limited by the number of registers used by a work item, the local memory used by a work group, and the number of concurrent work groups supported by the hardware. So okay, so now we have an idea of the programming model. So now um, we'll go to the details. And one more thing I want to tell. So we can only have reliable communication among the work items that are present in the same work group. It's not possible to have uh, reliable, well-defined communication between work items that are in different work groups. So that is not defined in OpenCL, at least until 2.0. So let's keep this restriction in mind. So we'll come back. We will encounter this later. Okay. So what's the compiler's role? So the compiler has to, given a data flow graph of tensors, the compiler has to do two things. One is it has to convert this data flow graph of tensors into data flow graph of OpenCL kernels. Um, and both these graphs are directed and acyclic. Uh, so these in inference mostly we will encounter these acyclic tensor computation graphs. So the compiler generates both the data flow graph of OpenCL kernels, and with for each kernel it also generates code for each kernel. So and each OpenCL kernel loads inputs from global memory, then computes, performs some computation on the loaded values, and then stores the result back to global memory. For instance, in this graph, in this figure, the left-hand side graph, there is almost one-to-one correspondence between the left-hand side graph and the right-hand side graph, except that this the node called convolution con is broken down into um, two nodes in this OpenCL kernel graph. That is I am to call and matmul. Other than that, we can see that, for instance, add corresponds to the add operation in the TensorFlow graph corresponds to the add OpenCL kernel, and ReLU corresponds to ReLU, like that. So, so, so now let's take a look at some of the optimizations uh, that can be performed on this OpenCL graph. So we saw that each OpenCL kernel loads input from global memory, then computes and stores to global memory. So uh, so one of the immediate optimizations that we can think of is fusion. So why is it important? Because interkernel communication happens through global memory, and the cost of that communication is proportional to tensor size, and it also requires temporary buffers. For instance, uh, because um, communication happens through global memory, so uh, so in this graph, only the output of the ReLU is visible to the outside world. All other outputs, like intermediate results, like the results of addition, matrix multiplication, I am to call, they are all stored in temporary memory, in global memory.
Arun, one question.
So we can see that this temporary the size of temporary buffer depends on is proportional to the tensor size. Also, we can see that we need a lot of memory bandwidth uh, to store these results, store these intermediate results, and load them back.
Arun,
So yes,
Mhm. Hi.
one question.
yes, Rupesh.
In this case, are all the tensor sizes known a priori at compile time, or are there possibilities of dynamic sizes also?
So no, they are. We assume that they are all known at compile time, Rupesh.
I see. Okay. But these could be arbitrarily large.
Right. Uh, right.
Okay. Sure.
Arun, yeah.
Yes. Yes.
Uh, by fusion, do we mean fusion of operators here?
Yes. Yes.
Okay, yeah, thanks.
Thank you. Yeah. So um, so the advantages of fusion is that we don't have to have one OpenCL, at least one OpenCL kernel per tensor operation. I mean, usually we may have multiple kernels also. For instance, convolution, we saw that it's translated into IM to call and matmul. So, 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 and so by not having by not having at least one OpenCL kernel, we also avoid the cost of uh, starting a kernel. So even that has a some runtime overhead. Starting a kernel also has some runtime overhead. So that's also one of the benefits of Fusion. So we can, in addition, we can avoid the cost of executing loads and stores, and we can do away with the some of the temporary buffers. Obviously, it's not possible to do uh, fuse all kernels, fuse all operations into a single kernel. Can you guess why it's not possible to? Why it's not uh, possible or advisable to? Why is it advisable to keep Fusion under a check?
Is it because of dependencies? Maybe like some operators, maybe if they are dependencies of two operators are different, then you may end up getting more loads and stores instead of lowering it.
Okay, I'm sorry, I didn't get it. Sorry, Sharwari, I didn't. Um,
So
okay.
is it possible, Arun, that by fusing the kernels, the resource requirement might turn out to be much more than what is reasonable from a GPU perspective, for
Yes.
example, number of registers or local memory?
Yeah. Yes, Rupesh. Yeah, that's a very good answer. So yes. So if we Fusion may increase the number of live in values in number of live values. So this will limit. I mean, this is the same. It's very similar to loop fusion, where we don't want to. I mean, it's good to in loop fusion. It's very similar to loop fusion, where if we fuse loops, then we can avoid loads and stores. But if we fuse the loops have higher um, higher register pressure, and they require more registers. As Rupesh said, this will limit the GPU's ability to do context switch. And GPUs, as we know, it's important to do context switching, because that's how we hide memory latency. So that's one of the reasons. And another thing is that if we fuse shared computations, then we may end up doing the same computation in two redundantly. So that's one of the these two are some of the performance considerations. So one another thing is that because of limitation of OpenCL programming model, so we saw that we can have reliable communication between work items only within the same work group. We cannot reliably communicate two work items in two different work groups, cannot communicate reliably in OpenCL kernel, OpenCL programming model. So uh, probably I think so. I don't know if Sharwari meant that, but for instance, if there is a dependency such that two work items in different work groups have to communicate um, to perform a computation, then there is no choice. We have to do these two operations in a um, uh, so the in different kernels, because uh, there is no reliable communication between work items in different work groups. So what we should do is those two work items should store the result in a memory, in a temporary buffers, and a new kernel will read the values from that temporary buffers and then compute the output. So this is one of the reasons why we can we for in this in this example we could in this example we see that IM to call is not fused with matmul, add and reload. So one of the main reasons is that the matmul kernel uses the value computed by two different work items in two different work groups of IM to call. So in many popular implementations, this will be the case. So that's why we cannot fuse them. Okay. So another thing is that uh, what Rupesh mentioned. So fusion may increase the number of live values. So and fusing complex operations like matmul poses some challenges. For instance, let's take this A equal to B dot C plus D, where B dot C is a matrix multiplication. So and so they are all vectors. Okay. So one of the so what happens is that how many registers are needed to do this. Assume that assume that let's take this simple operation like A equals B star C plus D, where star is the usual what is that usual multiplication. So how many registers do we need to do this? Assume a load stored architecture.
I would say two. One for loading B, one for loading C. Then we do the multiplication and store it in wherever we have stored B. And then we free up whatever it was C's register, we load D there, and then we add up that D to the register and store it in the same register, and then store it back to A.
Right. Yes. Yes. That's a register optimal way of doing it. So similarly, we have uh, similarly we have we face similar challenges in doing this for vectors. So what we in matrix multiplication, what do? We initialize the result to 0, and then do the we then and then we accumulate some, right? That's a normal way to do matrix multiplication, right? So
Yeah.
so instead of initializing result to 0 and then accumulating, if we directly set the result to, if we directly initialize the result to D and then if we accumulate, then we will save a register. So we will save some registers. So this is I mean so that way we can save registers. So the complexity is because um, because of how GPUs operate. So usually we have a loop that will compute the we have a loop that will compute the matrix multiplication, and then after exiting the loop, if we load from D and then add it to the result, it will result in more number of temporaries. So instead of that we just initialize the result to D and then uh, we do the accumulation. So that way we can save some registers. Okay, so another another thing that another interesting issue is that uh, uh, um, how do we manage memory? That is, how do we manage memory? So we saw that mainly interkernel communication happens through global memory, right? So these intermediate and temporary resources consume significant memory, and many computationally efficient convolution algorithms like FFT based convolution increase memory footprint significantly. Uh, why? Can you guess why FFT may increase memory footprint? Uh, uh, so I'll give you a hint. So in convolution, we will usually have a big image, and then we have a small filter, uh, and then we apply the and then we have a smaller image uh, I don't I forgot the name of that. What is that called? The smaller image. Can any convolution? So the big there's
Kernel.
huh?
There's input image and then one kernel which passes. Convolution kernel. Are you pointing to that?
Yeah, right. So there is a small image. We will that will slide over the whole input image. So in FFT based convolution, what we do is for FFT based convolution, the size of the image and that kernel, that small image must be the same. Okay, so what we do is we fill it with zeros. So that's why FFT based convolution will increase the memory footprint. So these computationally optimal algorithms will increase memory footprint significantly. So, and this is a real issue. For instance, we may not be able to run these algorithms because of memory limitations, and usually um, inference often inference happens in mobile devices and constrained resource constrained devices. So it's important for us to have a reduced memory footprint for our computation. So so
Hey, Arun, there was one question in the chat box related to the fusion. So one question on the limitation of the fusion: is there any correctness concern when floating point arithmetic is not associative? Is there a possibility of deviating from the desired value in that kind of kernel that you compute?
Yes, thanks, Ravi. Yes, that's a possibility. That's a valid. I mean, that's a valid concern. But so yeah, so if that's a big concern, then probably we shouldn't be doing fusion. So yes, we will be reordering computations. So that's possible.
Okay, so related question is, have you avoided fusion because of that in any of the experiments that you did?
No, Nikhil. We didn't. I mean, it didn't affect the accuracy. So it didn't affect the accuracy in our experiments.
Okay,
Usually,
thank you.
they'll the. I mean, uh, uh, see. Usually there'll be some resilience because usually this shouldn't be a concern. That's what I feel, uh, because I mean, there'll be the model would account for many errors. So usually that shouldn't be a concern here. But yes,
Okay.
it's possible that but your concern is right, theoretically at least.
Okay, thanks.
So we have to manage the physical memory that is present in our device efficiently. So how do we map the temporary buffers to physical buffers? So this is where in many ways it's similar to register allocation, um, but but okay, now let's look at the challenges. So I mean, let's look at the definition, what the compiler is trying to solve here. So our aim is to minimize the total size of OpenCL scratch buffers. So it's a different problem. It's a max coloring problem. So so we are not trying to minimize the total number of OpenCL scratch buffers, but we are trying to minimize the total size of OpenCL scratch buffers. And another thing is that constructing an interference graph from a data flow graph, um, that itself is an interesting problem. Here we are assuming that we cannot control the schedule. I mean, given a data flow graph, we can. There are many possible legal schedules for a data flow graph. So we are assuming that the compiler cannot control the schedule, how the operations will be scheduled. For instance, if two operations are parallel in the data flow graph, then the compiler will always assume that they may be executed in parallel because because it cannot control the schedule. So a different problem is what is the schedule we have to follow in order to minimize the total memories, total scratch buffers. So that's a different problem. What we are assuming that is that the compiler cannot control how operations will be scheduled. So yeah. So given a legal serialization of a data flow graph, then we can use the traditional definition of liveness, right? Because it will be a serial program, so we can define liveness in the traditional way. But how do we define the notion of liveness in the absence of schedule? So let me draw something on the board so that so please tell me if you can see the board.
Yeah, the board is visible to me. Those of you who have pinned the presentation, please unpin it so that you are able to see Arun's video. Yeah, Arun, go ahead.
Okay, so assume that so we have a fork join model of so this assume that this is the data flow graph. Can you see the graph?
Yes, yes, the diamond is visible.
Okay, Rupesh, not not what is inside the diamond.
That's a little difficult for me. I don't know about others.
Okay. Let's. Okay, that shouldn't matter. Okay, so A, B, C, D. Okay, this is the, assume that this is the data flow graph. Okay, so as we can see that these two nodes can execute in parallel, right? Because they are not, they are independent. So can we allocate the same buffer to, see, B will produce the result in a buffer and C will produce result in a different buffer. Can we reuse the same buffer for these two nodes? Please note that these two nodes can execute in parallel. So we cannot, right? Because if we allocate the same physical buffer to both B and C, then they will be overwriting their results, right? So we cannot allocate the same physical buffer to these nodes. Okay, so actually, but this is not all. So in general, we can have two all four possible combinations, like two nodes that are dependent, but they are not okay. Let's go one by one. Independent, but not conflicting. Then not dependent, not conflicting, not dependent, conflicting, dependent, not conflicting, and dependent and conflicting. So we saw the example of case 2, right, where two nodes are independent but they conflict. So we have other three cases also. We can have two independent nodes, but they don't also conflict. So the example is like example is concatenation of operation. So a concatenation operation copies just concatenates the results of two tensors. Okay, so we can see that and this the inputs to the concatenation are produced by some other nodes, like uh, say like so we have some okay, so like so assume that this is a concatenation operation, and so this one is 90 n1 n2. Okay, so we can see that this concatenation operation concatenates the buffers of n1 and I mean okay. Sorry. Yeah. So the concatenation operation concatenates the results produced by n1 and n2. So in this case, what we can do is even though these two nodes n1 and n2 are independent, we can make them share the same buffer by making sure that this n1 writes to n1 writes to first half and n2 writes to second half. Can you see this? So this way, it's possible for two independent operations to use the same physical buffer. So
Arun,
yes.
in this case, even the output sizes are known a priori, is it?
Yes, Rupesh. So see, we assume that the size of everything is known.
Okay.
So that's often a valid assumption. For instance, in object image recognition, we know what will be the size of the image that we'll be getting. So that's not an unreasonable assumption.
Sure.
So we see that two nodes which are independent, still they can use the same buffer. So it's also possible to have two nodes which are dependent, and yet they cannot share the same buffer. So I'll give you a hint that so let's assume a cast operation. So it casts the so we are doing a 32 bit casting a 32 bit number to a 16 bit number. So why we cannot why these two operations cannot share the same buffer? That's because assume that please remember that things are happening in parallel, right? So what happens is that okay, so this assume that there are four work items, each of them reading and then writing the each of them performing a read from the memory and then writing their output. So what happens is that if if we use the same if we use the same buffer, then what will happen is that okay, sorry, the it's a 16-bit to 32-bit cast. Okay, for instance, work item T0 thread T0 will read from memory 16 bits and then write write a 32-bit value. So similarly, T1 will also do that. If both of them share the same memory location, we can see that there is a race between T0 and T1. That's because T0 will T0 will read, say, from address 0 to 0. T0 will read from offset 0 to 1 of the input buffer, and it will write to offset 0 to 3 of the output buffer. And T1 will read from offset 2 to 3 of the input buffer, and it will write to offset 4 to 7. So can you see why is the race? Can someone tell me why there is a race between T0 and T1?
Is it because of the word boundary of 32 bits in the input?
Yes, Rupesh. So we can see that the read set of this right set. What is the right set of T0? It's bytes 0 to 3, right? So
Oh, I see. So 2, 3 is common to.
Yeah. So we are assuming that they share we are using the same buffer for output also.
For input and output, right?
Yeah.
Okay.
Yes. So we can see that there is an overlap between the write set of T0 and the read set of T1. So there is a race. So even though I mean, so we cannot have. So this is a case where two operations may be dependent. So two operations may be dependent, but still they cannot share the. They cannot share the same buffer. So this is one thing, and so what all these and what all we saw: dependent, non-dependent, not conflicting, that is copy concatenation, and non-dependent and conflicting, that is the usual parallelism case, and dependent, okay, dependent and non-conflicting is the usual case where, for instance, suppose that we have to do an add operation and then followed by a max or reload operation. Reload operation I think what it does is um, it, can someone tell what ReLU does? Or,
For
can,
negative values, it will give you 0. For negative value, it will give you 0. For positive, it will be linear, right?
right, yes, that if it is greater, if it is less than 0, it will make it 0, right?
Right. Yeah.
Yeah. So this case, in this case, it is possible to have the two operations share the same same buffer, um, because in this case there is no data race. So so we can see that. So I will turn off the video. So we can see that it's possible to have all four combinations of conflict and dependence. So so constructing an interference graph is a little challenging, but just think about it. We will be able to we will be able to tell when two nodes exactly interfere. Okay. So that's like a homework. So you just think about it, how we can do it. Okay. So and another thing is that we are solving a max coloring problem, not a min coloring problem. So let's all also think about the case where using more number of buffers can actually result in less I mean less total memory size. So just try to come up with a interference. Try to come up with a graph where we use more colors, but the weights of the but the weights, if I mean, we use more colors, but to get a optimal coloring, in the sense that the sum of the buffer sizes is minimum when we use more buffers. So you just try to come up with an example for that. So that's all I wanted to point out in this. So once we have a inference graph, then we can easily then we can use any heuristic to do the max coloring. So I have given an example in this, so I won't go into the details of this. So other optimizations are like broadcast optimizations, where so instead of reading when fusing broadcast operations, so we don't have to write. Broadcast operation writes the same value to different memory locations. So when we fuse broadcast operations, we don't have to write them to different memory locations and then read from different memory locations again. So that kind of optimization we can do. And then we can do, as we saw, we can eliminate concatenation altogether by allocating a bigger buffer and letting the operations which produce the result to cooperatively update the bigger buffer without any race. and then we can do copy propagation also, and constant folding is also possible for uh, some operations. For instance, in FFT based convolution, we know the uh, that small kernel, we know that's a constant image, so we can instead of doing FFT at runtime, we can compute it and store it. So these are some other optimizations that are possible. So just to conclude, compilers have a very big role to play in speeding up uh, um, inference in deep neural networks. So we just saw we just had a flavor of what kinds of optimizations compilers can do. So yeah, that's all I wanted to share. Thank you so much for your time. And uh, do you have any questions? Please feel free to ask.
Thanks, Arun. Any questions? Okay. I have one question, Arun, about.
Hi, Arun.
Sorry, Unnikrishnan, go ahead.
Yeah, like just to have a high level question, like how much you mentioned just now. I don't conclude the constant folding, So I just would like to know how much about other optimization like common expression elimination or local value numbering, and also how the fundamentals of abstract interpretation uh, analysis, like live in those things are very useful, or how much effective or in improving the code, or that's all.
Okay, hi Uni. Yeah, thanks for asking this. So actually, so these are some of the common optimizations that we found useful, Uni. So these were these were the things that we encountered in the examples that we saw, in the example networks that we saw. So, and as we know, I mean, as such, we didn't do any theoretical exploration of what is all possible. So we just uh, these optimizations were driven by the networks that we saw only. So we didn't proactively think about all different scenarios, and then and then so do you get what I'm saying?
Yeah, yeah, I got it.
Sorry, Uni.
Yes, yeah, I got it.
I think a lot of work is going on in that direction. So, what all the, I mean, I mean, they are defining execution models, and what kind of optimizations are possible. So that's a very happening work in this area.
Yeah. Okay. Okay. So,
Yeah, Arun, one quick question. When you were kind of you had this dependence graph and which you were offloading onto the GPU as far as different kernels are concerned. Did you also face any issue with respect to say load balancing or something?
Okay. Um, so Rupesh, actually we didn't have that kind of we didn't go so much deeper. So all that we had, I mean, the opportunity I had was for a limited time, say 1 or 2 years, and we didn't go how to control the, I mean, uh, we didn't try to control the schedule, we didn't try to do load balancing and all such things, Rupesh.
Sure, sure. No problem. That's fine. So it was more like Earlier it was not being done on the GPU and you wanted to give a working prototype on the GPU. Is that how it was?
Yes, Rupesh. So this work we did some 3 years back. So
I see.
I mean, so different APIs were coming, and we wanted to have we wanted to build a compiler that is that speeds up inferencing. So that was the setting which we had to which in which I worked. So
Sure.
obviously, I mean, I didn't go in, uh, to those details and also
Yeah,
scheduling.
no problem. No
So
problem. Although this,
yeah, we
whatever you
have.
have explained,
Uh,
whatever you have explained, that is still quite relevant even today. So I think it was good.
yeah. Yeah, so that those are interesting problems. So how to load balance, and how to create schedules that will minimize the buffers. For instance, we have in traditional compilers, we have scheduling that will minimize the register size, right?
Right.
By so that kind of possibilities are also here. So and this is a bit old work. So 2-3 years old work. So I think many there are many advancements, but yeah, this just gives a flavor of what can be done.
Right. All right. Any other questions anybody has? All right. So we'll stop here. And next week, Avnish is going to give a presentation. Thanks a lot, everyone, for joining.
Thank you all. Thank you, patient all. Bye bye.
Bye.